7 over 9 times 26 over 28 times 63 over 65 times 124 over 126 times etc., and off to infinity. Infinite product. So, what does this equal? Well, wait, hold up. What even are these numbers? What is the rule here? The rule is this: 8 minus 1 over 8 plus 1. 27 minus 1 over 27 plus 1. 64 minus 1 over 64 plus 1. 125 minus 1 over 125 plus 1. Okay, and what's the... Oh, I get it! 8, 27, 64, 125. Those are the cubes. The cubes. 2 cubed, 3 cubed, 4 cubed, 5 cubed. Ah, okay. So these are all the numbers of the form n cubed minus 1 over n cubed plus 1. Okay. And off to infinity. Infinite product. So, what does it equal? Man, I don't even know if this converges. I mean, 7 over 9, then 26 over 28, then 63 over 65. Yeah, those numbers are getting closer and closer to 1. Okay. Yeah, I reckon it converges. Probably. But then what does it equal? That I have no idea. Pause the video, give this problem a try if you want. Okay, it seems it is converging to something. 0.6666... Oh, it's 2/3. Yeah, it's 2 over 3. Converging really slowly, though. Taking its time. But yeah, definitely not going below 0.6 repeating. It's definitely 2 over 3. Okay, close this. It's 2 over 3. But how can we prove it? How can we calculate it? Let's go back. 7 over 9 times 26 over 28 times 63 over 65 times 124 over 126, etc., up to n cubed minus 1 over n cubed plus 1, times etc., and off to infinity. So, first of all, let's rewrite all the terms in their proper form. 7 over 9 is 2 cubed minus 1 over 2 cubed plus 1. 26 over 28 is 3 cubed minus 1 over 3 cubed plus 1. 63 over 65 is 4 cubed minus 1 over 4 cubed plus 1. And you get the point. 5 cubed minus 1 over 5 cubed plus 1, etc., etc. Okay, and now, we're not really multiplying infinitely many numbers here, right? It's a limit. The limit as n goes to infinity. Yeah, so the limit as n goes to infinity of this big giant product that I'm not going to say because it'll take too long, but it's not infinitely long anymore, it's a finite product. A finite product which stops at n cubed minus 1 over n cubed plus 1. Okay, so what can we do with this? Well, all the terms are in the form n cubed minus 1 over n cubed plus 1. So we could factor n cubed minus 1 and n cubed plus 1. I can't think of anything else. Okay, n cubed minus 1 equals n minus 1 times n squared plus n plus 1. And n cubed plus 1 equals n plus 1 times n squared minus n plus 1. Yeah, okay. And so when we divide them, we get this big fat factored fraction fruit loop. Yeah. And now we can split this big fraction into two smaller fractions, n minus 1 over n plus 1 times n squared plus n plus 1 over n squared minus n plus 1. Yeah, I guess. But now what? Well, believe it or not, that's it. That's actually all the tricky stuff we need to do. Yeah. Oh man, you're not gonna believe this. Put your socks on, get ready for some wicked mathematical sorcery. Hehe. So we start with the first term. 2 cubed minus 1 over 2 cubed plus 1. That's the special case in our formula when n equals 2. Okay, so plug in n equals 2 into the formula, and we get 2 cubed minus 1 over 2 cubed plus 1 equals 1 over 3 times 7 over 3. Okay, so I'll write that down. And next we do the second term, 3 cubed minus 1 over 3 cubed plus 1. That's the special case when n equals 3. Plug in n equals 3, and we get 3 cubed minus 1 over 3 cubed plus 1 equals 2 over 4 times 13 over 7. Yes, write that down too. Next up is 4 cubed minus 1 over 4 cubed plus 1. That's the case when n equals 4. Plug in n equals 4 into the formula, and we get 4 cubed minus 1 over 4 cubed plus 1 equals 3 over 5 times 21 over 13. Yeah, okay, and we do it again for n equals 5. For n equals 5, we get 5 cubed minus 1 over 5 cubed plus 1 equals 4 over 6 times 31 over 21. And you know what, let's just do one more term as well. N equals 6. Turns out to be 5 over 7 times 43 over 31. Okay, and of course it keeps going all the way up to the nth term, which is n minus 1 over n plus 1 times n squared plus n plus 1 over n squared minus n plus 1. Okay, next we're going to split these fractions into two groups. The first fraction, the third fraction, the fifth, the seventh, etc. Let's color those ones green. And the second fraction, and the fourth, and the sixth, and eighth, etc., let's color them blue. And then we'll put the green fractions on the left side, and we'll put the blue fractions on the right side. Yeah, like this. Okay, nice. Alrighty, now then, take a closer look at these numbers. Maybe you've already noticed, but these numbers are repeating themselves. Do you see it? There's a 3 here, and a 3 there. A 4 here, and a 4 there. A 5 here, and a 5 there. Okay. And for the blue guys, it's the same thing. There's a 7 here, and a 7 there. A 13 here, and a 13 there. There's a 21 here, and a 21 there. A 31 here, and a 31 there. Okay, but no way this is just a coincidence. Ha, no. There's definitely something sneaky going on here. Let's see. Well, for the green fractions, it's really obvious. The top numbers go 1, 2, 3, 4, 5, and so on, and the bottom numbers go 3, 4, 5, 6, 7, and so on. So both of them are just the sequence of integers. They're the integers, except the bottom one has been shifted backwards by 2. Yeah, it's been shifted back by 2. Okay, but we can just shift it forward. We can shift it forward and align the top and the bottom together. Yeah, so then we get 1 times 2 times 3 over 3 times 4 over 4 times 5 over 5 times ... all the way up to n minus 1 over n minus 1 times 1 over n times 1 over n minus 1. Yeah, but now all those fractions in the middle, they disappear. They cancel themselves away. 3 over 3, gone. 4 over 4, gone. 5 over 5, gone. All the way up to n minus 1 divided by n minus 1. Everything cancels, and all that remains is this 1 times 2 times 1 over n times 1 over n plus 1. Yeah, and we can simplify that if we want. May as well, I guess. 2 over n times n plus 1. Okay, very nice. Halfway done. Now we gotta do the blue side. But what's this? It's the same thing! Actually, it's even simpler. This 7 can cancel with this 7, this 13 cancels with this 13, 21 cancels with 21, 31 cancels with 31. All of these numbers can cancel. We just need to shift the top numbers over by 1. Let me just box them in first, like this. And there we go. Oh yeah. And then everything in the middle cancels. Goodbye. And all that's left is the 1 over 3 from the very start, and this n squared plus n plus 1 term at the very end. That's it. Tidy it up. N squared plus n plus 1 over 3. Wow, amazing. And if you're wondering why everything just cancelled so perfectly just then, the reason is because of this special term n squared plus n plus 1. Try this. What happens if you replace all the n's here with n minus 1? If you replace all the n's with n minus 1, something really special happens. It turns into n squared minus n plus 1. Okay, n squared minus n plus 1. But n squared minus n plus 1, that's also the bottom number in the fraction underneath the n squared plus n plus 1, over here. So it turns out, by a sheer miracle of God, both n squared plus n plus 1 and n squared minus n plus 1 are actually of the same form. But the bottom one is just what you get when you change the n's to n minus 1. Okay? It's the same, but it just gets shifted over by 1. And that's why it works. Yeah, okay. Anyway, where were we? Oh yeah, now we can just combine both the green and blue stuff back together. Put it back together, and we get 2 over 3 times n squared plus n plus 1 over n times n plus 1. Wow, look at that. Our big giant product turns out to be this really simple fraction. And 2 over 3. Ah, yes, I remember you. This is looking good. And the rest is just cake. Find the limit of this n squared plus n plus 1 over n times n plus 1, which is a really easy limit. First week of Calculus 101. Boring. It equals 1. So the final answer is just 2 over 3 times 1, which equals 2 over 3. Hooray! 7 over 9 times 26 over 28 times 63 over 65 times 124 over 126, etc. forever equals 2 over 3. Nice. But now I wonder, what happens if we do powers of 4 instead of the cubes? Or even powers of 5? Nah. Please subscribe to my channel. Bye.